Hello everyone and welcome to this training program on discrete probability distributions. My name is Vamsidhar. As a part of this session, let's look at what are the different types of probability distributions, the broad classification of the probability distributions, and what do I call as a probability distribution. First of all, what do I mean by probability distribution? Because earlier we have talked about the word probability. So from probability, how am I deriving this probability distribution? It's nothing but, in our earlier chapter we talked about a concept of random variable, which means any variable which has different outcomes, but that outcome, what particular outcome comes, is determined by chance and is purely random in nature. For example, if I throw a dice, I know the outcomes are 1, 2, 3, 4 and 5 and 6. But at any point in time, when I throw a dice once, I don't know which outcome will come. So such kind of variable, I'll define x as getting any of these possible outcomes. I throwing a dice, getting any of these possible outcomes. So what happens? The various possible outcomes that x can take. X is a random variable which can get the outputs as 1, 2, 3, 4, 5 and 6. And if I also write down the probabilities of each of them, which is nothing but the relative frequency of occurrence of each of them, either through the priori method or through the empirical method, whatever is the method, if I can write down the probabilities of each of them, and a table of this form is what we call as a probability distribution. So as we are mentioning here, it gives the probability for each of the values of the random variable. Now in this dice example, I know that the random variable is taking 6 different values, and the probabilities associated with each of those 6 different values. If I assume that the dice is a very logical kind of a dice, very unbiased kind of a dice, I can very well say that the probability is 1 by 6 across, because 6 possibilities and out of that 1 is a favorable one. So overall 1 by 6 will end up as a probability there. So this particular distribution I can express either in the table format or in a graphical format or in the method of a formula. Any of those three things can be expressed either in a tabular, as we have shown here. I can plot a graph by taking all the possible values on the x-axis. Probably I'll take 1, 2, 3, 4, 5, 6 on the x-axis, and I may plot either a line graph, right, joining all the points, something like a frequency polygon, or I can think of drawing a histogram, any of these things. So it could be in a graphical format, or in terms of a formula. I can write the probability of x equal to 1 by 6, where x is 1, 2, 3, 4, 5, 6, and it is equal to 0 for all the other values of x. So this is the formula mode of expressing the random variable, the distribution associated with the random variable. So there are three different mechanisms in which a probability distribution can be expressed, but in a simplistic sense, probability distribution is nothing but all the possible values which a particular random variable can take and their corresponding probabilities. Now based on this phenomenon, we have to differentiate whether a random variable is discrete or continuous. When I say discrete, I can very well count how many possible outcomes can come out. We know in case of a dice, only 6 possible outcomes are there. Right? In case of a tossing of a coin, only 2 possible outcomes are there. In some cases, what happens is the number of outcomes or number of values which a particular random variable can take is very much finite, or it is countable. Even if it is infinite, even if it is very large, I have a mechanism to count it. It could be a few thousand, but still I have a mechanism to count it. Whereas if I ask a question, what are the heights of the people? So if I take a random variable x as the height of a person, I can, in some cases I may make it into a nearest integer, but in some cases if I take the data as it is, then obviously there are infinite possible values depending on the kind of scale I can use for measuring the heights of the people. There could be infinite possible values: 160 centimeters, 160.1, 160.09, 160.011, any kind of value depending on the number of decimal places I am taking. All the values are possible, which means I may not be able to count what are the total number of possible. Even if it is large, I cannot count what is the total exact number of values which can be taken by that random variable. In that case, we call such kind of random variables as continuous random variables, and any probability distributions associated with such a kind of random variable, we call them as continuous probability distribution. Whereas in this chapter our focus will be primarily on discrete random variables, which means I know how many outcomes are going to be there. Even though they are very large, they are countable. So wherever the number of outcomes are countable, we will be dealing with how do I identify the probabilities of each of those outcomes and form those as a part of a table or a graphical mode or even a formula kind of a mode. So that is what is a discrete random variable saying. Now let's try to link up how we relate it with statistics. Now these random variables, look at them, the values taken by the random variables, look at them as the class intervals and the corresponding probabilities as corresponding relative frequencies. And so we can come out with mechanisms on how do I find out the mean of the random variable. I can find out the variance or the standard deviation of this kind of a distribution. And why are we doing this entire exercise? Finding the patterns in the data. Depending on the frequency distribution or relative frequency distribution, what did we do? We have identified the chart pattern, and based on the graph pattern, we can very well make out the centeredness of the data or the dispersion in the data. That is what we have looked at in our previous chapter. So this probability distribution table or graph also will help us in identifying the shape of that specific distribution, the centeredness of the data, and even the dispersion in the data. So what happens is, for every aspect we end up, once a probability distribution is in place, which is in this format, we either end up finding out the probability of one specific event, one specific outcome occurring. Like what is the probability of getting a 4? One specific event occurring, we may have one kind of a formula for it. Or we can end up finding out the mean of this kind of a distribution and the variance and standard deviation of this kind of a distribution. The same way which we have done in case of frequency distribution, if this happens to be a class interval, for finding out the mean, what we have taken is the midpoint of that class interval. So here I don't need to take the midpoint. Here I am taking the actual values which can be taken by my random variable. This is what is the linkage I can do with the frequency distribution and a probability distribution. In a frequency distribution, for all the possible classes, we have found out how many occurrences or what is the proportion of the occurrences in my data. Whereas when it comes to probability distribution, again for each of the possible outcomes, what is the chance of occurrence of those outcomes? So there's a lot of similarity between a frequency distribution and a probability distribution in this manner. Now, this chapter will focus primarily only on discrete random variable and discrete probability distribution. There are two important, though there are so many discrete probability distributions. The most common probability distributions which we will be focusing on slightly later in this chapter are only two of them. One is called as binomial distribution, and the other one is called as Poisson distribution. These are the kind of distributions which are very heavily used. We'll discuss what is the specific pattern that is associated with each of these distributions. But just as a quick recap from whatever we have discussed in the earlier chapters, whenever we talk about the word probability of occurrence of any event, we have to be very clear that the value of probability should always lie between 0 and 1 for any specific event. 0 and 1 are also inclusive. 0 and if a probability comes out as 0 or if it comes out as 1, then it is like a definite event, definitely possible or definitely impossible kind of an event. Whereas if anything lying between 0 and 1, there is some level of uncertainty assigned to the occurrence of that particular event. Then if we are talking about a probability distribution, what we are saying is the sum of all the probabilities should be equal to 1. Then only we call that particular probability distribution, that particular tabular or equation form as a probability distribution. Now here if we see, this is 1 by 6, 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 and this is 1 by 6. Now the sum of all these probabilities is equal to 1. Then we call it as a probability distribution. If that sum does not come out to 1, then we can, or if it is more than 1, then we don't call that to be a valid probability distribution. Let's say if someone says x equal to 1, 2, 3, 4 and p of x equal to 1 by 3, 1 by 3, 1 by 3, 1 by 3. Now if I add up all the probability, it is coming to 4 by 3. It's not coming up to 1. Then I cannot call this as a probability distribution. These values can be different. It's not mandatory that all of them should be the same. Probably I can have another scenario where x is 1, 2, 3. The probability of x, this is 1 by 2, this is 1 by 3, and probably this is 1 by 6. Whatever may be the probabilities, if I add all the probabilities, it has to be 1. And each of them individually should be lying between 0 and 1 inclusive. Only in that case I am calling that particular table or that particular graph or that particular equation to be a probability distribution. And depending on any common patterns that are there in this kind of a data, in the probabilities, okay, are they uniform? Or are they going up and falling down? So depending on the patterns which are being observed between the probabilities of various values, different names have come up. When I use the word binomial or Poisson, they are nothing but we see some kind of a pattern in the probabilities. So any specific, some kind of most common patterns have been identified and they have been given the names, so that whether even if we are interested in finding out the mean or variance or standard deviations of them, we can easily find them out, because once a specific name is identified, a couple of formulas are also associated with those calculations. We'll move forward and see. But in general, any probability distribution that is given, which means if I say a probability distribution is given, then it means there is the values of x, the different values which the random variable can take, and their corresponding probabilities. So if I have anything of that kind, I can very well find out the mean of that probability distribution. Let's take one example to address all these things. If I say x equal to 0, 1, 2, which means x can take a value of 0 or 1 or 2. Taking a 0, the probability is 1 by 4. For 1, it is 1 by 2. And for 2, it is 1 by 4. 1. Now, this is a probability distribution because all the probabilities are lying between 0 and 1. And we are also seeing that the sum of all the probabilities is equal to 1. So, I can very well take that this is a valid probability distribution, even if it is in a tabular format. Now, for every distribution like this, I'll have a mean associated. The way I find out the mean is the weighted average. I do 0 into 1 by 4, which means each value, the different value multiplied by its corresponding probability. 1 into 1 by 2, 2 into 1 by 4, and add them up, which is nothing but 0 into 1 by 4 plus 1 into 1 by 2 plus 2 into 1 by 4, which is actually, let's say, coming up to 1. So what I say is the mean of this particular distribution is equal to 1. So any probability distribution, if I want to find out the mean, it is nothing but the random variable multiplied by its corresponding probability. This mean in a probability language is also called as the expected value. So the in probability language, mean also means expected value. So which is found out by the weighted average. And couple of things I have to understand. The mean can be greater than 1. Probability will lie between 0 and 1. But the mean or expected value can very well be greater than or equal to 1. Or it could be less than 0. Any value is very much possible for the expected value. So don't or it could be even a decimal. Even though all my possible values of x are integers, there is a good chance that my mean can very well be a decimal also. So mean, there is no restriction on the possible values for the mean. That is one point we have to remember. The only for the probabilities we know that it is lying between 0 and 1. But computation of the mean, there is no specific boundaries for the values of the mean. So every possible value of the random variable, multiply it with its corresponding probability, we up and do a summation that would result in mean for any probability distribution. Now, instead of doing this entire calculation, if I observe that this particular distribution is a binomial distribution or a Poisson distribution, instead of doing this weighted average multiplications and all, the process is simplified. That is the reason we identify them as specific patterns by identifying specific names to them. Otherwise, for any distribution, this is the way, whether I can identify a name to it or I cannot identify a name to it. If I want to find out the mean value, the average value of this particular distribution, then I'm doing a simple multiplication of the different values of the random variable multiplied by their corresponding probabilities. And then going back to the variance or the standard deviation for the same example, x is taking values 0, 1, 2. P of x was taking values 1 by 4, 1 by 2 and 1 by 4. And we were able to find out that the mean is going to be 1. Now, if I want to find out the variance, a simple calculation what I suggest is from every possible value of the random variable, subtract the mean. Just like we have done in case of an individual scenario. 0 minus 1 whole squared. Subtract the mean, square it. Then multiply it with its corresponding probability, 1 by 4. Similarly, the second one, 1 minus the mean whole squared, multiply by its corresponding probability. Then similarly 2 minus the mean whole squared multiply by its corresponding probability. And then add them up. 1 into 1 by 4, which is 1 by 4. The second term will become 0 and third term is 1 by 4. So I'll say the variance is 1 by 2. And we saw that the standard deviation is nothing but square root of variance, which will give me 1 by root 2. This is what is the value associated with the standard deviation and the variance. Now, all we should understand in this entire exercise is the variance is nothing but once I compute the mean, I subtract the mean from each of the individual values, just the way we have done in case of the distribution also, statistical frequency distribution also. Subtract each value from the mean, do a square. Instead of taking a weighted average there, I'll do a multiplication by its probability and then add up, because probability is nothing but a form of weighted average itself. So this is the way we can find out the mean, variance and standard deviation of any distribution, because these are the most important aspects even as we move along for doing a lot of conclusions about the statistical world. So we have to be very comfortable in the usage of these words of mean, standard deviation and variance. Now, that particular slide was for any distribution. Now we are moving into specific distributions. As a part of this chapter, we'll deal with two such kind of distribution. One is binomial, two is Poisson. In binomial, the pattern which we are observing is, if at all I know how many times a particular experiment has been conducted. Let's say we are talking about an experiment. For any experiment, only two outcomes are there, success and failure. Let's say I toss a coin. I will get two outcomes, head and tails. If I can define head means success, not head, which is tails, is failure. So the all set of outcomes, let's say dice. What are the outcomes? 1, 2, 3, 4, 5 and 6. Now if I can say 1 and 2 means success and remaining 4 is failure. Either way, if I can split the entire set of outcomes into success and failure, they could be equal in number, they may not be equal in number, there could be only one value in success, remaining values in failure, whatever it is. Whatever is worth for me to observe, for whatever the thing I want to find out the probability, if I can associate a success to that and the rest of it being a failure. So any trial, any experiment I am doing, I should be able to find out, I should be able to find what is success, what is failure in that. First point, I need to know what is the probability of success and what is the probability of failure. So if I say in this example, I'll say probability of success is 2 by 6 and failure is 4 by 6, assuming they are uniformly possible. So the success probability is 2 by 6, failure probability is 4 by 6. So one thing is, any experiment I should be able to identify what is a success and a failure, and then I need to identify what is the probability of success and what is the probability of failure. Then I need to have a scenario. I repeat the same experiment n number of times, which means I throw this dice 20 times or 15 times. I repeat the same experiment n number of times and I have to get x successes, which means success is nothing but getting a 1 or a 2 in this example. So if I throw a dice 15 times, what is the chance that I will get 1 or 2 3 times exactly. What is the chance of getting a success 3 times? Which means, simplifying it, I should be able to find out the probability of X successes of an experiment which is repeated, and for each experiment I know independently what is its success and failure. I am repeating that experiment n number of times, and once I repeat the experiment n number of times, I should know what is the chance that R successes can come up. Let's say a simple example. I know that the chances of me clearing an exam is 80% and failing is 20%. Now I am interested, I am writing 10 exams. If I am writing 10 exams, what is the chance that I will pass in at least 8 subjects, 8 exams? Which means probability of 8 successes as well as 9 successes as well as 10 successes. And because there is OR relation, we'll use the probabilities addition rule here. So that's how, so this kind of scenario is getting classified as a binomial distribution, especially when there are 2 outcomes to the, any number of outcomes, but I can split that entire number of outcomes into success and failure. I know exactly the probability of a success and the probability of a failure. I want to repeat that experiment n number of times, and I want to know how many, what is the chance of getting X successes. That is what we associate to a binomial probability distribution. And if I know that particular distribution is a binomial distribution, then the probabilities are directly calculated with this formula NPX. So NPR is what we have already found out, n factorial by NCR. So NCX into P power X into Q power n minus X. This is the formula. So we know NCX from our permutations and combinations formula, n factorial by n minus x factorial into x factorial. Then P is the probability of success. Here 2 by 6. 2 by 6 to the power of x number of successes into the remaining. Q is the probability of failure, which is 1 minus P. So which goes as 4 by 6 to the power of the remaining number of failures. So the probabilities. So when I know 1, 2, 3, 4, I'm throwing the dice 5 times. So I may get 0 successes, 1 success, 2 success, 3, 4, 5. These are the possible values of my random variable. And now I want the probabilities. If I know that this is a binomial distribution, I can find out each of these probabilities using this formula. The probability of getting 0 successes, substitute x equal to 0 and n equal to 5, and you will get the probability of 0 successes. Similarly, probability of 1 success, 2 successes, and probability of n successes. So we should always remember that x as well as p both are pointing to success. P is the probability of success and x is the number of successes that we can get when we are repeating the experiment n time. So a couple of things that need to be understood in this context is, what is the probability, what is success and failure, what is the probability of success and what is the probability of failure, and if I am repeating the experiment n times, what is the probability of getting x successes. If I have these kind of scenarios, I can very well use a binomial distribution and I can very well find out the probabilities of occurrence of each of the different possible random values, random variables, and once I have the distribution, I can easily find out the mean and the variance of that distribution also. In simplified terms, The mean for a binomial distribution is simply NP. N is the number of trials, P is the probability of success. Variance comes out as NPQ. N is the probability number of trials, P is the probability of success, and Q is the probability of failure. So once I know the variance is NPQ, the standard deviation is simply root of NPQ. So I don't need to actually form a distribution and then do a multiplication of the various values multiplied by its corresponding probability. All those things I don't need to do to arrive at the mean and then the variance, provided I know that particular distribution is a binomial distribution. So you should be able to identify in your business logics, is this particular kind of data following something like a binomial distribution? Can I classify the outcomes as success or failure? And if I can know the success and failure, what is the probability of success and what is the probability of failure? Can I identify the probabilities of success and failure? And out of n number of items, what is the chance of getting x successes? If this kind of a situation is created, then we can very well associate to a binomial distribution. And once it's a binomial distribution, we should be able to find out the mean and the variance of the binomial distribution very easily. Then moving on to the next one, which is the Poisson distribution. In the Poisson distribution, the requirement is like this. When we are more interested in finding out the x number of events occurring, the number of occurrences of a particular event in a particular interval. It could be a time interval, it could be a distance interval, it could be a volume interval, or whatever it is. What is the chance of a particular event occurring x number of times in a particular interval? So that is what we are calling it as a Poisson distribution. The moment I know what is the x number of events occurring in a particular interval, if that is the kind of a requirement, I can very well find out the probability of that number of occurrences, x number of occurrences, using the Poisson distribution. So generally the scenario goes with, if at all the probability of success or it is the Poisson distribution is specified by a parameter called mu or lambda, and if lambda equal to something, we'll see in our next slide, the lambda or mu is related to the binomial distribution using a factor called NP, which is nothing but the mean of the distribution. So if at all the number of experiments is very large and the probability of occurrence of each of the events is very, very small, then the binomial distribution will also approximate to a Poisson distribution, which is given by a parameter called lambda, which is nothing but equal to NP. So assuming that that is the scenario, if at all I want to find out the probability of a particular event occurring x number of times in a specific interval, time interval or a volume interval or whatever it is, then we are using the Poisson distribution. So here the scenario is, I want x number of occurrences, which is what the scenario even in a binomial, but the only difference here with x number of occurrences is, there I am talking about n times the experiment has been repeated and I want x number of occurrences of that success. Whereas here I don't know how many times I am repeating that experiment. In a particular interval, I want x number of successes. So this is one prime difference between a Poisson distribution and a binomial distribution. And what we are seeing is, once I know that it's a Poisson distribution, the probability can be found out, the probability of x number of successes can be found out using this formula. Mu power x, or sometimes instead of mu people use lambda, anything is fine. Lambda power x into e power minus lambda by x factorial, and e is what is approximately equivalent to 2.718. Using this formula, people will find out the mean or the probability of occurrence of x number of successes in a specific interval. And once I know that it's a Poisson distribution, again I don't need to end up finding out the mean as the multiplication between the values and its corresponding probability. I can simply say mu is the mean of that, and mu is also the variance of that. The moment mu is the variance, I know standard deviation is square root of mu. So the moment I know that that particular data is following a standard, a Poisson distribution kind of a pattern, again the mean and the variance of that Poisson distribution are standard in nature, which is equal to mu or lambda. And as I said, the key difference between a binomial and a Poisson is, in a binomial distribution, we are always repeating the experiment n number of times, whereas in case of Poisson distribution, we can have any number of occurrences. See, if I am repeating an experiment n number of times, the maximum possible value in a binomial is only n. Whereas here we assume in case of Poisson, the experiment is repeated almost infinite number of times, which means the number of possible values is also infinite, but it is countable. So there is a probability of occurrence of each of these events. So typically a binomial will boil down to a Poisson, especially when n is very large, an experiment is repeated so many times. The probability of an occurrence of an experiment, of an occurrence of a success, is very, very small. P is very, very small. In the sense, NP will go much, much lesser, below 10 itself. In that case, I can approximate a binomial distribution to a Poisson distribution, taking a lambda or mu to be equal to NP, and find out the probability of occurrence of one success or two successes or 10 successes during a specific interval. That's the kind of similarity we can build between binomial and Poisson. And of course, apart from binomial and Poisson distributions, there are so many such kind of discrete probability distributions. We have a negative binomial distribution. There are so many other forms of discrete probability distribution. But in this chapter, we'll confine ourselves to the binomial as well as Poisson distribution. So we have to clearly identify what kind of cases fall under the binomial distribution, what kind of cases fall under the Poisson distribution. And once we identify something as a binomial or a Poisson distribution, how do I find out the probability of occurrence of x number of successes out of n possible experiments? Or if I cannot express some specific thing as a binomial or a Poisson distribution, then we can resort to the normal procedure of finding the mean and the variance, because at the end, once I have a data in place, I am converting it into a frequency distribution which is equated to a probability distribution. And once I know a particular probability distribution, I should be able to find out the characteristics of the data using the mean and the variance. So that particular aspect should be clear to you. I hope you are comfortable with the concepts of binomial distribution, Poisson distribution, or a general probability distribution, and the concepts of mean, variance of each of these distributions. If you have any further queries regarding this, please feel free to contact me on the phone number given below, 9848012123. You can also mail me at vamsidhar@pacegurus.com. I suggest you visit our website www.pacegurus.com for any updates regarding the training and consulting assignments in the areas of finance, investment statistics and analytics using tools like Excel, VBA, and SPSS. I hope this session is useful for you in terms of application of various probability distribution concepts. Thanks a lot for listening to this session. Thank you very much.